This is a compilation of paradoxes, riddles, and optical illusions that will blow your mind.
Puzzles and illusions give us a fascinating look into the human mind. Look at this 4x4 matrix. Can you find the missing number? I'll give you the answer at the end of the video. In a world saturated with information, our brains are constantly seeking new ways to engage and entertain themselves. One of the most captivating phenomena that capture our imagination are riddles and optical illusions. But puzzles do more than just amuse us. They reveal the complex and fascinating workings of our minds. So what is it about riddles and optical illusions that our brains find so irresistible? Let's dive into the science and psychology behind our love for these mental challenges. Let's start with a riddle. Imagine you're in a room with 3 light switches, each corresponding to one of 3 light bulbs in another room. You can't see the bulbs from where the switches are. How can you determine which switch controls which bulb if you can only enter the bulb room once? Before I reveal the solution, why do we care enough to even want to solve this riddle? Riddles like this engage our cognitive functions on multiple levels. Our brains are hardwired to seek solutions, a skill animals and humans developed early on in their evolutionary timeline for survival. When faced with a riddle, we are immediately thrown into a problem-solving mode, activating areas of the brain associated with logic and reasoning. Often, riddles require us to think outside the box and come up with creative solutions. This engages the right hemisphere of the brain, known for handling creative and spatial tasks. And finally, solving riddles often relies on our ability to remember details and recall them accurately. This strengthens our working memory and improves our ability to manage multiple pieces of information simultaneously. Solving puzzles ultimately engages multiple parts of our brain, both those of pleasure but also survival, which give us a dopamine hit when we eventually solve them. So, do you know how to determine which switch to choose? Let's solve the riddle. Pause if you still need a second to think. Here's how you do it. Turn on the first switch and leave it on for a few minutes. Turn it off and immediately turn on the second switch and leave to enter the room with the bulbs. The bulb that is still warm corresponds to the first switch. The bulb that is on corresponds to the second switch, and the bulb that is off and cold corresponds to the third switch. If you solved it, did you feel that dopamine hit when we confirmed the solution? That's our brain trying to ensure that you continue surviving and positively reinforcing your good work. But let's consider another. Think about the famous checker shadow illusion. In this illusion, there are 2 squares labeled A and B, which appear to be different shades of gray. But they're actually the same color. The surrounding context of the image tricks our brain into seeing them differently. Optical illusions like this fascinate us because they reveal gaps in our perception. Again, our brain is programmed to seek out ways that it's wrong so it can improve its reasoning. Or at least most people's brains are. That said, our brains are designed to make sense of the world quickly and optimize pathways, often using shortcuts or heuristics to interpret visual information. When these shortcuts are tricked, it highlights several key points about our cognition. First being pattern recognition. Our brains constantly look for patterns to make sense of what we see. Illusions exploit this tendency, leading us to see things that aren't there or misinterpret what we do see. Context also matters. The context in which we see something significantly impacts our perception of it. The checker shadow illusion demonstrates how our brain relies on context to interpret shades and shadows, often leading to incorrect conclusions. Finally, there's the way our brain adapts. Optical illusions remind us that our perception is not always accurate, but it is adaptable. Our brains can learn to interpret ambiguous information more accurately the more we're exposed to them, which is what makes us want to keep coming back to optical illusions. Both riddles and optical illusions tap into our brain's reward system. When we solve a challenging riddle or understand an illusion, our brain releases dopamine, a neurotransmitter associated with pleasure and reward, like I mentioned before. This release not only makes us feel good, but also reinforces our desire to seek out more puzzles and illusions. So let's try one more puzzle. Arrange the numbers 1 through 9 in a 3x3 grid so that every row, column, and diagonal adds up to a total of 15. Pause here if you want to try and solve it yourself. Now let's reveal the solution. Solving this puzzle provides a sense of accomplishment and satisfaction, highlighting the role of dopamine in our love for puzzles. Again, if you solved it, did you feel that dopamine hit? But what about the first matrix I gave you? Let's solve it now. To find the missing number, we have to first observe the pattern that the numbers in the matrix are arranged in a sequence of prime numbers, being that each number is only divisible by 1 and itself. The matrix is filled row by row with consecutive prime numbers. We thus have to determine the prime number that comes after 41 and before 47, that being 43. Again, this challenges our brain's ability to pick on patterns, whether learned or perceived, and fill in the gaps to the solutions we need. Riddles and optical illusions are more than just entertaining diversions. They are windows that we can use to look into the complexities of our cognitive processes. They challenge our problem-solving abilities, engage our creativity, test our memory, and reveal the quirks of our own perception. Most importantly, they activate our brain's reward system, making us eager to tackle the next challenge. So, the next time you find yourself captivated by a tricky riddle or a mind-bending illusion, remember that you're not just having fun. You're giving your brain a delightful workout. And who knows, you might just uncover something new about the fascinating world of your own cognition. When scientists start pondering the bizarre reality of infinity in nature, some perplexing things start happening. If the universe extends infinitely in any given direction and there are infinite stars, then the night sky should be as bright as the sun, right? This is known as Olber's paradox. The concept of this paradox essentially breaks the sky into sections or points in order to account for stars at varying distances from Earth. Assuming an even distribution of stars throughout the sky, there would be 100 times the number of stars at a given point at 10 times the unit of distance. This slightly confusing mathematical proposition boils down to the conclusion that every point in the sky, regardless of the number of stars, should collectively be the same brightness. We can trace the origins of this paradox all the way back to Kepler in 1610, though it wasn't popularized until the 19th century by a man named Heinrich Olbers, a German astronomer. In large part, the paradox demonstrates a proof that the universe is not static or infinite. Since we do know that the night sky isn't as bright as a star in every location, we're left with many questions that aren't as easy to answer as you might think. Astronomers and scientists have to explain Olber's paradox in 5 possible lines of thinking. Dust is accumulating, obscuring distant stars and causing dark spots. There are, in fact, not an infinite number of stars. Stars aren't evenly spaced across the universe. The universe is expanding, so distant stars disappear thanks to a concept known as redshift. Or the universe is too young to see the most distant stars. Addressing these in order, we're left to understand how cosmic dust might obstruct parts of the sky and create the illusion of darkness here on Earth. While the theory of dust blocking light makes sense on Earth, in space, dust would just block or absorb the light energy from distant stars and would itself start to glow or produce light. This is the reason why nebulae glow when they don't have an internal energy source. Assuming then that the universe has a finite number of stars is a valid conclusion, but it doesn't solve the paradox. It could theoretically be possible that the universe has a finite number of stars, but just the number of stars we can see in the observable universe is enough that the night sky should be fully illuminated. Astronomers currently estimate that there are 100,000 million stars in the Milky Way alone, and roughly 10 to the power of 24 stars in the entire universe. While that number isn't infinite, it's enough that it doesn't explain the paradox. Next, we move on to ponder whether maybe the stars aren't evenly spaced across the universe. Perhaps they group together and form clusters that look like singular stars in our night sky. This solution is the first that could be correct when looking into it further. There's no definitive reason to think that stars would be evenly distributed, and perhaps they do in fact clump together, leaving large chunks of dark sky. However, just like that question you annoyingly got wrong on that high school science test, that answer probably isn't the most correct. The likely solution was discovered in 1929 by Edwin Hubble when he discovered that the universe is expanding, leading way to the understanding that the universe is likely finite in nature. Part of the way Hubble made this discovery was by realizing that we can measure the speed at which things are moving away by focusing on how the wavelength of their radiation has shifted. This is known as redshift. We understand that galaxies that are further away from us are moving faster, so it's possible, if not probable, that their light has been redshifted far down in the light spectrum, no longer visible to the naked human eye. Coupled with this likely solution, it's also probable that the universe as a whole is too young to see the most distant stars. Essentially, the universe is only estimated at 13.7 billion years old, so we wouldn't be able to see any objects further away than 13.7 billion light years. This means that our observable universe is as far as we can see, and the darkness comes from the absence of the light that we can't see. These two final propositions to explain the darkness, redshift, and a too young universe present the most likely solutions to the Olber's paradox. Now, thanks to the Olber's paradox, the next time you look up at the night sky, you'll wonder not about the beauty of the stars you can see, but about the beauty of those that you can't. Napkin rings. Probably the last objects on Earth that you would expect to completely blow your mind today, but get ready because they're about to. When you core a sphere with a cylinder, you're left with an object that looks like a napkin ring of a certain height. No matter the size of the sphere, if you perform the procedure to create a napkin ring of a certain height, every ring that height will have the same volume. But that probably doesn't blow your mind yet because it's a little abstract. So let's bring this abstractness back to reality to demonstrate it further. When you core an orange to create a napkin ring, you're left with an object that is probably about 2 inches high. If you then core the Earth to create a napkin ring that is also 2 inches high, you're left with two seemingly different napkin rings, except they have the exact same internal volume. This is called the napkin ring paradox. The math that proves why this bizarre phenomenon occurs isn't really that complicated, but it is math. For that reason, I'll do my best to explain things in the simplest way possible. In order to find the volume of each napkin ring, you have to subject yourself to formulating some equations that use the area of a circle, a little geometry, and the Pythagorean theorem. What you'll find is that after going through all of the math, you're left with an equation that looks like this. v equals pi times h cubed over 6. One thing you'll notice if you look at the equation is that in order to solve for the volume of a napkin ring, all you need is the height of the napkin ring. In no way is there the radius or the diameter in that equation. It turns out that the radius of the original sphere cancels out in earlier equations as you're deriving this final one, and it's ultimately inconsequential to a napkin ring's volume. If you're curious about how that equation was formulated, I'll link to Vsauce's video on this topic in the description below because he goes into a far more in-depth discussion of it. So what does all this mean? All this mathematical wizardry ultimately poses some perplexing paradoxical comparisons that can be made in the real world. Pushing this paradox even further to the extreme, if you were to core a golf ball and the sun, each to have a resultant height of 1 inch, those two rings would have the exact same volume. What about a pea in Jupiter? As long as the napkin rings have the same height, the resultant volume will be exactly the same. This problem actually dates back to the 17th century, first recorded to be found by Japanese mathematician Seki Kowa. His geometrical proof eventually was formulated into the modern-day napkin ring paradox, which gained popularity from its ultimate perplexing nature. So, what does all this geometric hocus-pocus mean to you specifically? It doesn't really have any grand implications other than now you can blow your family's mind. Zeno's famous paradox of Achilles and the tortoise focuses in on the hero of the Trojan War, Achilles. This famous warrior is engaged in a race with a slow-footed tortoise who is granted a 100-meter head start. Initially, Achilles thinks that he will make easy work of the tortoise, but a problem arises when he tries. Achilles starts running, eventually catching up to the position of the tortoise in a certain amount of time. But in that time, the tortoise has moved an additional 5 meters. Now, Achilles is behind by 5 meters, and he moves ahead to try to close the gap. In the time he does this, the tortoise has moved another 1 meter. This continues to happen, and the gap continues to get smaller and smaller. But yet, Achilles is never able to overtake the tortoise. We obviously know that Achilles could overtake the tortoise, but it seems that the situation proposed by the paradox is also fully plausible. It might be easy to dismiss the paradox as philosophical nonsense, but understanding it presents an interesting look into the mathematical principle of divergence. As we seek to wrap our minds around the paradox, we first have to understand that the argument is sort of a complicated trick. Zeno first proposed the paradox as a complicated proof that motion does not exist. In other words, that we should try to deny the principle of motion, which sounds absolutely absurd. But the paradox reveals an obvious disconnect between how we perceive the world and how the world actually works. Nonetheless, motion exists, but the paradox reveals that explaining how motion works isn't quite as simple as we may think. The entire paradox is rooted in the idea that there is an infinite number of gaps that Achilles must make up, meaning that he will be infinitely stuck behind the tortoise. The thing is, not all infinities are created alike. Infinity is essentially a series of numbers, and there are two kinds of series: divergent and convergent series. The series presented in the paradox starts with 100, then shrinks to 5, then to 1, then maybe to 1/2, and so on. In this sense, Achilles is engaged into an infinite series. The assumption we make, however, is that the infinite series diverges, or results in a whole number. The series 1, 2, 3, 4, and so on diverges as it equals infinity. However, the series Achilles and the tortoise are engaged in converges, meaning that it does come out to a whole number if you sum all of the series up. The number added onto Achilles' travel distance gets smaller and smaller, and thus the total distance traveled converges to a number that is equivalent to the distance of the tortoise. In this idea lies the answer, and the original confusing nature of the paradox. If we interpret the initial paradox as a suggestion of a divergent series equating to infinity, then Achilles will never catch the tortoise. However, when we understand that the series of the paradox is convergent, we see that the mathematical and logical model of the paradox eventually matches up with our view that Achilles will overtake the tortoise and win the race. Proposed by Bertrand Russell in the early 1900s, the Barber Paradox introduces a town where every single resident must be clean-shaven. There exists a barber in this town who only shaves residents who do not shave themselves. These statements may seem simple at first, but a paradoxical proposition arises. Who shaves the barber? The ground rules of the paradox are as follows. The barber is one who shaves all those, and those only, who do not shave themselves. Number 2, everyone in the town must be clean-shaven. There are a few minor additional assumptions as well. 1, that everyone's face grows hair and thus needs to be shaven. 2, that the barber needs to be shaved. And 3, that the townspeople can only shave themselves, no one else. If the barber shaves his own face, then he shaves someone who also shaves themselves. This breaks the initial rule that the barber can only shave people who do not shave themselves. However, if the barber does not shave himself, then he breaks the second rule, stating that everyone in the town must be clean-shaven. The question then remains, who shaves the barber? Despite the paradox's popularity, it's actually not even a paradox in the pure sense of the word. A man who shaves exactly those men that do not shave themselves, by definition, cannot exist, and consequently, there's no reason to expect otherwise. Understanding this assumption provides an answer to this paradox and gives the source as to why it's so infuriating. There is no answer. It's impossible. The answer to the Barber Paradox is just that. The statements themselves are equivocally false. Bertrand Russell created the paradox to examine our understanding of classes and groups in logical theory. In the end, he stated that in its original form, the Barber Paradox is just noise without meaning. In this, his intention shines through, to create logical noise that appears paradoxical but is simply impossible.